Diffraction grating and single slit diffraction.
A diffraction grating consists of a large number of equally spaced narrow slits and are created by etching thousands of thin lines onto a glass slide. They produce maximum and minima just like in the double slit experiment. Here's the graph we had earlier. You can see the maximum lines, the maximum intensities, and the intensity falls off very smoothly. But the pattern is much, much sharper because instead of just 2 slits in the double slit, I have thousands of slits in the diffraction grating. The more lines or slits there are, the narrower the peaks are. Also, if we were to shine white light on a diffraction grating, we'd get a spectra of all the colors. Since, as we're about to find out, the location of maxima depends on the wavelength, and the colors in white light separate out, just like dispersion, which we showed earlier when we were talking about prisms and rainbows. Here are 2 examples of what a diffraction grating will show. If we put a diffraction grating up and we pass through the spectra from excited xenon gas over here, we will get very discrete lines here. You can see the green lines here, blue, violet, red, very discrete patterns. If we were to pass through white light, like from the sun, we will see all the colors and they'll be smeared together. You can also see this effect by looking at a CD, if you have any anymore, or a DVD at an angle, because they're created by etching cuts into a polycarbonate plastic disc. When you do the math, you come up with the equation for the maxima for diffraction grating is the same as for the double slit experiment, where we have m is the order, lambda would be the wavelength of the incident light, L is the distance between the 2 observation screens, and D here is the distance between the individual etchings. Of course, with a diffraction grating, this is much, much smaller than the distance between the 2 slits in the double slit experiment.
The distance that the light is diffracted, which is x right over here, depends on the wavelength, lambda. Shown below is a diffraction pattern for green light. If white light is used instead of green, then each color gets diffracted a slightly different amount because all the colors are different wavelengths. White light is diffracted as shown below. You've got the white right in the middle, and then your first order maximum is there, second order maximum, third order maximum, and notice how they get spread out and their intensity goes down a bit. The lines on a diffraction grating are so closely spaced, it is often easier to cite the number of lines per centimeter or millimeter than to specify the distance d between the lines. So to calculate d for a diffraction grating with 500 lines per millimeter, because after all, d is in all our equations, first you convert to lines per meter. So 500 lines per millimeter times 1,000 millimeters per 1 meter, right? That's just equal to 1. That's a conversion factor. And what cancels? Millimeters. And we get lines per meter. So that's 5 times 10 to the 5th lines per meter. Invert the result to get meters per line, or the distance in meters between one set of lines. So you have 1 over 5 times 10 to the 5th lines per meter. That's equal to 2 times 10 to the minus 6th meters per line. So, a diffraction grating with 500 lines per millimeter has a slit spacing of 2 times 10 to the minus 6 meters. So that's our value of D. The distance between etchings on a diffraction grating is 2 micrometers, and the distance between the grating and the observation screen is 3.5 meters. What is the distance from the midpoint of the screen to the first order maximum for light with a wavelength of 580 nanometers? We write all our givens, being sure to convert micrometers to meters. 1 micrometer is 10 to the minus 6 meters, and nanometers to meters. 1 nanometer is 10 to the minus 9th meters, and we're looking for the first maximum, so m is equal to 1. Here's our equation. Substitute in our givens, carry out the math, and you get 1.02 meters. A diffraction grating with 6,000 lines per centimeter is placed 2.5 meters from a screen. What is the distance from the midpoint of the screen to the first order maximum for light with a wavelength of 700 nanometers? with our givens, we'll convert nanometers right away to meters, right? 1 nanometer is 10 to the minus 9th meters. But let's look at this term right here. 6,000 lines per centimeter is not d, which is needed in our equation. We need to convert this number into the distance between the lines. So a little unit conversion, 6,000 lines per centimeter times 100 centimeters per meter. There go the centimeters. So that's going to be 6 times 10 to the 5th lines per meter, but we still need a distance between the lines. So you take the inverse of that. So 1 over 6 times 10 to the 5th lines per meter is 1.67 times 10 to the minus 6 meters per line. And what's that equal to? D. So let's go to the next slide to finish the problem up. Now we can go to our diffraction grating equation here. And the first maximum, m is equal to 1. We found d on the previous slide to be 1.67 times 10 to the minus 6. So now we put in our lambda, our L, and we get x is 1.05. When light strikes a single slit, interference occurs between the individual waves that together make up the wavefront. Light wavefronts are incident on the single slit on the red line. So we've got the picture here. This is a little tricky. These all look like straight lines, right? However, if you look close enough, each line is composed of multiple little wavefronts there, okay? So there it looks like there's 3 or 4 of them. Each one of those will be interfering. So each individual wave spreads out as it passes through the slit and interferes with the other individual waves, right? Whenever you have a gap like that, diffraction, let me draw it over here. If you have the wavefront coming in here, it hits this gap and the wave regenerates. Now what we're having here is there's a multiple amount of these little waves hitting the gap, and they'll interfere with each other. We'll look on the next slide. Hopefully that'll make it maybe a little clearer. This will create an interference pattern with a wide, bright central maximum and secondary dimmer maxima. In this case, the geometry allows us to calculate the locations of the minima, as opposed to the double slit case where the maxima locations were calculated. Now the math's a little above this course, but we'll do that in advanced physics classes. Here's where the minima are located. M lambda L over D, where M is equal to plus or minus 1, plus or minus 2, etc. Because of the symmetry, the first maximum this time is located at x equals 0, and its width is equal to 2 times x1. That's the location of the first minima. So that's 2 lambda L over D. And over here, here's where we're showing these wavefronts breaking into individual waves that are then regenerated and will interfere with each other when they get to this point. Now obviously there's many more than 3, but we just wanted to show the example there. And frankly, that's how you do the math to come up with this equation. And here's a graph of the intensity. You've got a very wide, intense maxima. See the brightness there? And then you have other maxima, and look how the intensity falls off quite sharply. It gets very dim as you get farther away from the central maximum. The intensity pattern is the plot on the right side of the experimental setup shown below. Here's the intensity pattern here. We talked a little about that on the previous slide. As the width of the slit, your slit over here, becomes smaller, the width of the central maximum increases. As the width of the central maximum becomes wider, the image is more smeared out and images become more difficult to resolve. That is why an eagle's eye is so large and why telescope lenses are so wide. And what does that do? That makes D larger. And if you make D larger, then the width of the central maximum decreases. So that makes it possible to see greater image detail. It's less smeared out. In a single slit experiment, the width of the slit is 1.8 micrometers, and the light of wavelength 480 nanometers passes through and strikes an observation screen 0.92 meters away. How far is the first dark fringe, or minima, from the center of the screen? Start again by listing the givens and converting micrometers to meters and nanometers to meters. And we want the first dark fringe, so m is going to equal 1. Single slit equation, exact same equation as double slit, except this time what are we doing? We're finding the minima, not the maxima. So we substitute in our givens right here. Here's the 1 for first order. And the first minimum, also called a dark fringe, same thing, is at 0.245 meters.